12.6 is all about this thing called the binomial theorem. Now, expressions like a plus b is what we call a binomial, and in theory at least, it's very easy to raise a binomial to a power. If we had 2x minus 3 and wanted to cube it, in theory, you just write it out 3 times and do repeated distribution over and over and over again. The idea is pretty simple, but it can get tedious at times, especially when the powers get bigger. What if I want to raise something to the 5th power, to the 7th power, to the 20th power? There needs to be a way to find these expanded expressions without having to do repeated distribution over and over and over again. And to do that, it's just like what we've been doing with sequences, looking at patterns. So let's go ahead and see if we can't find one by looking at various expansions of powers of binomials. Now these patterns I did ahead of time, so I knew what they are. We're not going to spend the time just to FOIL everything out. But let's see if we can't find a pattern. See if you can spot a pattern. Suppose you had a plus b raised to the 1st power. Now that's trivial. A plus b to the 1st power is itself. A plus b. What if I squared it? Again, on the side, before the video, I already did this on scratch paper. I wrote it out twice. I FOILed it. You would have gotten a squared plus 2ab plus b squared. What if you cubed it? It's a cubed plus 3a squared b plus 3ab squared plus b cubed. What if you raised it to the 4th power? You would have gotten a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. What if you raised it to the 5th power? A plus b to the 5th power plus a to the 5 plus 5a to the 4th b plus 10a cubed b squared plus 10a squared b cubed plus 5ab to the 4th plus b to the 5th. That was a pain in the butt to do. And, oops, it should be a plus, it should be an equals. So on, and so forth. Now, there should be some noticeable patterns in the behavior of the exponents. So I think the easiest way to dissect this is to take it one part at a time. After all, a binomial, 2 terms, consists of 2 pieces. The a I consider as the first piece, and the b I'll consider as the second. So let's see if there is a pattern with the a terms in any expansion. Let's just choose the 4th expansion, for example, here. So I'm just going to highlight all of the a terms. Now, by highlighting, I hope it's quite obvious what the pattern is. Let's just read it from left to right. We start with a to the 4th, then go to a cubed, then a squared, a, and no more a's. Is that true for any expansion? We go. Let's do this one here. This has lots of stuff to look at. I'm just going to highlight the a terms. So I'm going to highlight the exponent as well. So, a plus b to the 5th power. Let's just focus on the a terms. You go a to the 5, a to the 4, a cubed, a squared, a, and no a. So it seems like, at least for the very first terms, right, the observation that we see that the exponents of a decrease. Again, I'll since these are notes and I did a lot of erasing, let's just write it one more time for posterity's sake. For example, a plus b to the 5th power, a to the 5 plus 5a to the 4b. I'm just copying it down. Plus 10a cubed b squared plus 10a squared b cubed plus 5ab to the fourth plus b to the 5. If you just focus on the exponents here of a, there's really a 1 here. You know, it goes 5, 4, 3, 2, 1. And not surprisingly, it goes in the exact reverse for the exponents of b. Observation: the exponents of b increase. For example, I'm just going to copy again, a plus b to the fifth power, a to the 5 plus 5a 4b plus 10a cubed b squared plus 10a squared b cubed plus 5ab to the fourth plus b to the 5. They increase. So you have no b's on the first term, so the first term has 0 b's. Then you have b to the 1, move on to b squared, move on b cubed, b4, b to the 5. So that's actually a pretty easy pattern to know, that when you're squaring a binomial, as you progress through the terms, the first term of the binomial will get all of the exponent first, and then you gradually decrease it by 1. Whereas the second term starts with none of the exponents, and then you gradually increase it up. But that isn't the whole pattern, right? We've looked at patterns of the a and the b terms, but we notice that there are these extra numbers that we sort of glossed over. Where do those numbers come from? Well, it turns out that to determine these coefficients, there is a pattern. What is that pattern? Well, what I want to do is take all the coefficients of this expansion here, right? So the coefficients, just the numbers. So here we have 1 and 1. Here we have 1, 2, 1. We have 1, 3, 3, 1. What I want to do is write those coefficients without the a's and the b's. So let's go ahead and do this. All right. So what about the coefficients? So if you were to do, let's start with to the 0 power. Of course, that's going to give us an answer of 1. A plus b to the first power, the coefficients were 1a and 1b. A plus b squared, the coefficients was 1a squared, 2ab, 1b squared. A plus b cubed, the coefficients was 1a cubed, 3a squared b, 3ab squared, 1b cubed. What was a plus b to the fourth power? It was 1, 4, 6, 4, 1. What was the coefficients a plus b to the fifth power? It was 1, 5, 10, 10, 5, 1. This pattern here is called Pascal's triangle. It's called Pascal's triangle, even though this triangular formation of numbers was written and discovered well before Pascal's time. That's history for you. Even if you didn't invent it, if you're more famous, hey, it magically becomes yours. And it turns out that these coefficients have a very interesting additive process. Every single number is the sum of the two adjacent numbers before it. What I mean is, how do you get this 4 here? It's just 1 plus 3. How do you get this 10 here? It's 6 plus 4. How do you get this 3 here? It's 2 plus 1. So Pascal's triangle is a very easy way of filling in these numbers in front, because whatever power you use, that's what row you choose. So what if I wanted to find the coefficients of something cubed? You do the Well, I guess technically it's the fourth row because you always have this extraneous number 1 here. Basically, this second element will tell you what row you're in. So if I want the third power, you use the row where 3 is the second number, so on and so forth. So this gives you a pretty nice way of figuring out the coefficients, and it gives you a pretty nice way of expanding things out. Now, let's prove it. I'm going to do a plus b to the 7th power. Now, this is something I haven't done yet before in scratch paper. We're doing it live right now. But I do know for a fact that it's going to be a to the 7. 7 gets a gets all the exponents, and then it's going to go down progressively. I'm going to leave a space here for the coefficient. A to the 6. Let's go ahead and do both at the same time. Then I know b is going to start off at 1. And then we have a to the 5, b squared, plus space, a to the 4, b cubed, plus space, oh, I'm running out of room here. Let's see if I can't write this smaller. Actually, let's do this. Yay, technology. Plus ab4 plus a squared b to the 5 plus ab to the 6 plus b to the 7th. Right. Now, doing the exponents was quite simple because, again, the powers of a should start at all the exponents and just go down by 1. And the exponents of b should start at nothing, there's no b's here, and then just increase by 1. Now, all I have to do is figure out the coefficients. So to do that, I need to do Pascal's triangle to the 8th row, or until this number is 7. So let's just continue from above here. So what do we have here? I'm going to put a line here to indicate that we're stopping for the notes. So then this would be 1, 6, 15, right? 10 plus 5 is 15. That's 20. 15, 6, 1. We start with 1. 7, which is what we want. What is that? 23, 35, 35, 21. I can't do math. This should be 21, and 7, and ends with 1. So there we go. We have the coefficients, right? So this is simply 7, 21, 35, 21, 7. Did I miss something? 7, 21, 30. Oh, I missed the second 35. 35, 21, and 7. Whew. There we go. That is the full expansion. Now, I've been doing things just generically with A's and B's, but it works the same way when you do non-A's and B's, if you have numbers in it. For example, suppose I ask you to expand 2x, I don't know, let's go backwards and let's do a minus 3x to the 5th power. So the idea here is to note that the a will be the first term, b is the second term. Notice how we have a minus here, so b is going to be negative. So a is 2, b is negative 3x. So we know that if we do a binomial to the 5th power, it's going to be a to the 5 plus a 4b plus a cubed b squared plus a squared b cubed plus a b to the 4th plus b squared, or b to the 5th, excuse me. Now, using Pascal's triangle from above, right, we know the coefficient will be 1, 5, 10, 10, 5, right? 1, 5, 10, 10, 5, yep. And then all you got to do is substitute. Therefore, 2 minus 3x to the 5th power is a is 2, and b is negative 3x. That's it. So I'm just going to literally rewrite this guy, but do the substitution. Is it a bit of work? Yeah, but I promise you it is a heck of a lot faster than doing all that foiling over and over and over again. Running out of room. Actually, let's use the technology thing and move it back. There we go. To negative 3x to the 4 plus negative 3x to the 5. And of course, you do have a little bit of work to do. You have to simplify it. This is 2 to the 5th. So that is 32. If you were to multiply all this guy together, 2 to the 4th is 16. Bring out a calculator here. Times it by 5, times by negative 3 is negative 240x. And then if you multiply all this guy out, you're going to get a positive 720x squared. Multiply this guy all out, so that's 4 times 10 times negative 27. That's a negative 1080x cubed. Multiply this guy out, so that's a positive 81 times 10. So that's a plus 810x to the 4th. Then finally 3 to the 5th, that's 243x to the 5. Right, so there you go. A little bit of work. You know, it's not instantaneous. It took us about 30 seconds, a minute. But again, a heck of a lot faster than writing out 5 times and expanding it. So pretty neat thing that you can do here. So expanding a binomial shouldn't be mysterious. It's a bit of work, but faster method than writing out repeatedly just to multiply over and over and over again. It just takes practice, guys. In summary, when you expand a binomial, the exponents of the first guy will take all of the exponents and then start decreasing by 1. The exponents of the second term will start with 0 and increase by 1. But you're always going to have numbers in front of every term. How do you figure out what those numbers are? You can construct this thing called Pascal's triangle, so that once you figure out the pattern to the exponents, you can just plop the coefficients in its place. And then, of course, if you do have actual numbers and variables, once you substitute everything in, you just, figure out the math. So that's the binomial theorem. Pretty cool, pretty fun, awesome. Good luck.